So now I'll hand over to Elia Kaufman, who will talk about their work on learning vehicle models for agile flight. Elia,
okay, I start by sharing my screen.
Yes.
So, you should see my screen now, I guess.
Yes, I can see your screen.
Okay, great. So welcome everybody to my short presentation today about learning vehicle models for agile flights. I'm Elia Kaufmann. I'm a PhD student at the Robotics and Perception Group from the University of Zurich. So let's see if this works or not. So yeah, in recent years, fast navigation of autonomous, research on fast navigation of autonomous quadrotors has made tremendous progress. So soon, estimation and control algorithms will reach the level of maturity that is required to push these platforms to their physical limits. This presents the need for quadrotor models that can predict the forces and torques acting on the platform, even during highly aggressive maneuvers. However, obtaining accurate models in that part of the state space is very challenging. So obtaining an accurate model of a quadrotor while it's flying very fast is challenging because of the complex and nonlinear aerodynamic effects that are at play in these parts of the state space. So just a short recap, when we speak of a model, we mean something that takes a current and possibly a set of past state observations of the vehicle and outputs a force and torque vector. Having an accurate model of the platform is beneficial for a variety of applications. Since a better model reduces the sim to real gap, it benefits, for example, controller design. It can be combined with deep reinforcement learning to train policies that better transfer to the real world. And yeah, if you actually want to transfer to the real world, we can reduce the likelihood of a crash when you already have a good simulation in the first place. So how exactly do we approach the task of accurate quadrotor modeling? Our method, we call it NeuroBEM, combines the benefits of machine learning with classical first principle modeling. Specifically, we use blade element momentum theory. You cannot see my mouse. The blade element momentum theory here illustrated at the top to model single propellers, and then augment this prediction of blade element momentum theory with a neural network, here illustrated at the bottom, that is trained on the residual forces and torques. The combination of these two yields a model with high accuracy, but requires fewer training samples than a model that is purely trained from data. Also, due to these first principle models, we show that the model generalizes better than approaches that are only data-driven. To train and test this NeuroBEM approach, we recorded over 1 hour and 15 minutes of flight time in one of the world's largest optical tracking volumes. The resulting data set contains very aggressive flights with accelerations of up to 4G and speeds of up to 18 meters per second. Our results show that NeuroBEM is able to simulate the forces and torques acting on the vehicle with unprecedented accuracy, as shown here on the right in the top plot. So the first table compares the root mean squared error of forces and torques, where fit is a very simple model. That is commonly used, for example, in the rotor S simulator. Polyfit is a state-of-the-art baseline which is purely learning-based. Our approach clearly outperforms both these baselines. When we use our model, here illustrated in the bottom table, to conduct virtual flights, this means we perform a specific trajectory in the real world and then refly this trajectory in simulation and see how close we get to the state evolution that we observe in the real world. We can see that again, our model outperforms both baselines by a significant margin. To illustrate this in a video, so you can see this video here. So in this video, you can see a green drone, which is a real experiment. This means the green drone illustrates what we have observed in our real tracking, in the real world, measured in the tracking volume. Then we illustrate in blue what our approach is able to simulate, and we can see that the blue drone is consistently closer to the real measurements than, for example, the yellow, the gray, or the red drone, which illustrate the baselines. So this video shows that our quadrodo simulator is significantly more accurate than anything published before, and it's well suited to reduce the sim to real gap. So yeah, that's already it. So if you're interested in this work, it's going to be published very soon at RSS 21, and the data set and the code will be published open source. So if you want to train your own models on it, if you want to use the simulator, for example, for your own research, it's going to be open source very soon. If you have any questions, just ask now or visit the interactive session or drop me an email. So yeah, thanks a lot for your attention and see you soon.
Thanks, Elia.